You'll have to go ahead and forgive my voice. I'm not used to talking this much, so it's kind of... Really, I thought I'd get more laughs than that. All right, everybody. Good morning. My name's Jim. I do Wi-Fi. Every once in a while, I do Wi-Fi right. This presentation is not about me doing Wi-Fi right, which is kind of odd because the last time I did a WLPC presentation, it was about how I did Wi-Fi wrong. So, back in May of 2023, I stood up at Mobility Field Day 9. Was it 9 or was it? I don't know. It was a Mobility Field Day 9. And I used my uber confident sounding radio voice, and I said a lot of things. And one of the things I said, Peter McKenzie came up to me afterwards, and he's like, I think there's a problem with what you said. I went, okay, let's talk. And that led to my presentation in Prague. And then between Prague and now, we've talked some more. And so what I found is in that time between May of 2023 and today, I have to go back to this slide because what I'm finding is it's more and more common. My first assumption is incorrect. So if you ever worry about being, you're like, oh, I was wrong about something. Hey, I have made more mistakes and I've been more wrong than anybody in this room. So what I wanted to talk about today was actually basically an antidote to the Wi-Fi 7 marketing machine, because there is a lot of misconceptions. There is a lot of things that we don't know, things that we're unsure of, things that we don't know what we don't know. And so what I wanted to come here today was to sort of update everybody, especially the people that I stood up in front of in May in San Jose and said some very incorrect things. And I wanted to bring this back to the community and say, okay, this is what we've been saying. This is what we've been saying since May. And now let me tell you what we're actually learned after dealing with this for a while. So if you've seen me present, you've seen that some of these slides or a version of this slide. And so what I wanted to do is I wanted to take some time this morning and I want to go back through these slides, and I'm going to make some updates for you, and we're going to talk about it, and we're going to talk about like all these great and magical things that Wi-Fi 7, if you're taking a picture of this slide, you probably should wait. Remember, this is what I used to think I think, and now I don't think I think that anymore. So I'm going to go ahead and deconstruct this, and we're going to have an antidote to the Wi-Fi 7 marketing machine, which unfortunately, I have to admit, I am marketing adjacent. So let's start with what Wi-Fi 7's called. Extremely high throughput. Now, we get this extremely high throughput based on a couple of key features. One of them being 4K QAM, 16 spatial streams, 320 megahertz wide channels, and we put all that stuff together. We throw it into the mcsindex.net mathematical formula. You shake it up, you spit it out, and then you get these numbers. And so that's what the marketing people get a hold of, and you go, hey, with Wi-Fi 7, I'm going to get 18 bajillion gigabits per second, and you're going to be able to live stream the whole, Library of Congress data in 3 seconds. Yeah, you laugh because you know, but there's a lot of people who don't. So let's talk about 16 spatial streams real quick. And I'm not going to talk about anything less than 16 spatial streams because I'm not ready. So we'll just get that settled down. 16 spatial streams, I think David Coleman said this, you're never going to see them. They're there in the standards. They're there. It's like, oh yeah, you can do 16 spatial streams. But when you start thinking about what the size and the power requirements for running something like that, it's just not going to happen. Let's just move that out because that's done. Next one I want to talk about is 320 megahertz wide channels. Now, some of us are fortunate enough to live in the land of milk and honey, and we were granted 1200 megahertz of spectrum. So we go, yes, we can do all the 320 megahertz wide channels we want, right? That's what my marketing boss would tell you is, oh, 320s. Well, If you don't live in the land of milk and honey and you only got 500 megahertz of spectrum and 6 gigahertz, how many 320 megahertz wide channels can you fit into 500? It might sound complicated, but the math is actually quite simple. You can't. You get one. So if you want to do more than one AP, you're not going to get 320. So now I'm happy to report that 4K QAM, yay, we still have it. It's a thing. We get it. But the other ones, mathematical constructs. So let me change my little chart here and go, what can you kind of expect depending on a lot of other variables? It depends is still a thing. Thank you, Sam. But again, when you take a look at these charts, one of the things you'll notice is there is a very direct correlation between channel widths and speeds. And so I was having this conversation with Devin a few nights ago, and it was like, well, but if you can't run 80s because you end up with a lot and you're looking at 40s. And so when you take a look at these numbers right here, you have the 0.7 and the 1.4, depending on how many spatial streams you have. You just take that number, you can see from 160 to 80, you go from 1.4 to 7. So what's half of 7? 350. If you're running 40s with one stream, 350. If you're running 40s with two streams, 700. Now it's still a lot when you think about it, because what we're doing is we're adding a third radio into the AP that already has one, at least two. Maybe you turned off the 2.4, but now you're adding this additional overhead on there. I'm not saying you're going to consistently see over 1 gigabit per second on your Ethernet link, but it's something to think about. So that's really kind of where we are with the data rates. We're not going to get to 46, 48 bajillion gigabits per second. Sorry, it's just not going to happen. So let's put that up to bed. I want to talk about the next feature that I've been confidently talking about, which is punctured transmission. This is the idea that if an interferer is in your channel plan, pops up, it's there, and we can carve out those RUs. It's a multi-RU feature. You can carve those out and you say, you know what, we're just going to block those. We're going to just take those out of our channel plan, if you will. We're going to drop those RUs, and we're still going to use the spectrum that comes up around it. That way we can, we're not burning the spectrum that lives above that by just saying, oh, we're just going to all revert back to 20 megahertz wides. Now, I'm happy to report this is still a thing-ish, because there's something I learned, which was this little puncture thing, for the time being, at least for us, it's a fixed definition. It's not something that it will do dynamically on the fly. Now, that's being worked on. I have to imagine there's probably some other people that might be dealing with the same thing that's coming, but make sure you pay attention to your vendors. Make sure you're paying attention to how they actually handle this, because when this first comes out and you first start installing them, it's probably not going to work the way that you want and think and hope, but know that it's coming, know that it's being worked on. So that's kind of good. We didn't really lose a whole lot there. So now, this is the one that kind of led to my entire presentation, multi-link operation. Now, a few weeks ago on Slack, there was a question that was asked about MLO. And they said, does MLO mean that we have full duplex in Wi-Fi? Now, what followed was, crickets, because nobody on the Wi-Fi Pro Slack has any opinions about anything. And so, no. What actually happened was our good friend Fernay went on a rant. Now, I would like to say that well, here's the thing. Fernay did it, so I didn't have to. So I was like, you know what? I'm just going to go with what he said, because I don't have to create it. But more importantly, what Fernay did was he actually showed some examples, which means I didn't have to go pull them, so thank you. So if you're drinking the Kool-Aid, which I'm hoping this is part of the antidote of your marketing Kool-Aid, MLO has some considerations, we should say. And Fernay spells it out pretty good here. If this is your 2.4 gigahertz spectrum, and this is your 5 gigahertz spectrum, and you're hoping to do MLO, but you have this 6 gigahertz spectrum, And your 6 gigahertz availability looks something like this chart. Thank you, Fernay. I didn't have to go put this together. It's just these random assortments of, well, not random, but spectrum, and then when it's approved. And as he points out, the availability of that spectrum being released for your country, for whatever country the network's in, is kind of slow and painful. I don't believe he's saying that 6 gigahertz is slow and painful, although it is kind of painful. But the process and getting it and doing it has been slow and painful. He is right there. And he summed it up and he said, well, for MLO, you're SOL. And the vast majority of the but I think it was funny what he said here at the end, because he said, well, and I think everybody in this room would agree that Fernay is very humble. So you are correct, you are humble. But I think we can all also agree that Fernay is not ignorant. Fernay basically did all this for me. But I want to kind of take what he said and I want to build upon it for a second. And we're going to finish out this conversation. There's 3 modes of operation with MLO. There is link redundancy, which is the idea that we are going to send the data frames out 2 different radios, same data. And we're going to send them out 2 different radio links, because that way, if one of the radio links takes a hit, our data still gets through on the other one. So that's the redundancy. That gives us a lot of resiliency. The other one is link aggregation, kind of like a lag port. You're like, oh, I got this one. I'm going to just lag those things together, and we're going to send half the data out one side, half the data at the other side. We're going to do all this stuff, and we're going to get all this magical stuff. And then there's link selection, which is latency. Link selection is the idea that the radio in your device is going to select which link it wants to use at that time based on the operating conditions of the environment at that time. But as Fernay pointed out for us, trying to get both of them firing up at the same time is going to be kind of difficult. So let's go ahead and remove these 2. But now I want to focus on the one we have left, which is link selection and latency. So this was a picture I took in our QA labs last summer at some point. And there's lots of different things, and we were doing all kinds of testing. But more importantly, what I realized is I took a picture of my laptop. And when we zoom in on that laptop, this is what the 6 gigahertz network looks like in there. Now, I point this out because in Fernay's example, there was no APs. There was no networks. So it is nice and open and clean. But that's because it hasn't really been deployed a lot. But as these start getting deployed, it is very possible, almost highly likely, that 6 gigahertz is going to start looking like this. This is what it's going to look like. But the other thing that I want to point out is if we take these 2 and we look at them kind of side by side, what you'll notice is there are a lot of networks. And now you can't see it on the one on the right, the 6 gigahertz in our lab, but the 5 gigahertz, there's a lot of beacons. But do you notice what there's not a whole lot of in this picture? There's not a whole lot of data. There's not a whole lot of traffic. So there's beacons, there's networks happening, but there's also, we got some stuff firing up here. We got some stuff down in here. This looks a little dirty and messy. Got some stuff down in here. But then you take a look at like this middle section right here, the top half of Uni 2, there's networks there. There's not a whole lot of traffic. But with link selection, what that allows our client devices to do is to actually pay attention to it and go, yeah, there's a lot of beacons, but there's not a lot of traffic. I can switch. And if 5 gigahertz loads up all of a sudden, I can switch over to 6. If 6 loads up, I can switch back to 5 if 5's okay. So it's giving the clients now have this ability to switch back and forth between those 2 bands, picking which one's going to give it its best opportunity to get the data through and get that ACK that we're all desiring so that we don't have retries. So of all of these, all the features in Wi-Fi 7, this one particular one is the one that I am most happy about, I'm most interested in, and I really want to see this working. But unfortunately, we have to get some networks that look more like this screen and less like the one that Fernay showed. So let's go back here. Let's talk about what we're left with now. So it's not full duplex. Fernay's right. I'm hoping we get there one day. There's some RF stuff that happens inside the devices that, might be a challenge to deal with, and because it's a physics issue and it's not any other type of issues, it might take us a little bit of time to overcome that one. The other one is not multi-AP. Now, in some of the original 802.11be drafts, there was a feature in there called multi-AP. Multi-AP is the idea that your device is going to be able to talk to one AP on one channel that's over here and another AP that's on another channel over here, and be like, oh, I'm going to talk to both of them at the same time. Now, this was pushed. So this is no longer in the BE standard. So when it's ratified eventually someday, that won't be in there. However, it hasn't been rejected. It hasn't been, anything like that. It's just been pushed. So there is the possibility that you'll see about this in the future. The last thing I want to point out is my drawing. This device that we're showing here is still 2x2. So in Ferne's first comment about using all three of the bands, 2.4, 5, and 6, there's only 2 radios. Now they'll swap and they'll switch and they'll go back between, their software so they can switch the bands, but you still only have 2 of them in the device. So they can't talk on 3 channels, 3 different spectrums, because there's only 2 radios. So what you're going to see is you'll never see 3 because there's just not enough radios. If you only have, some people would say I have 2 mouths because I can talk that much, but I don't have 3, so I can only talk to 2 people at the same time, not 3. So just keep that in mind when you start seeing some of this stuff that comes up as you start deploying 6 gigahertz and Wi-Fi 7. MLO, I have high hopes for. I'm really hopeful for it, but it's still only 2x2. So let's talk about the last one. Now, if you watched my mobility field day presentation, or if you were there in the room, I told this story, and I think it's worth telling to this group. When they wanted me to present this, I went to our standards guys, and I said, hey, if I'm going to talk about it, I want to make sure I'm using the right term. I want to actually sound like I know what I'm talking about and use the correct terms. I said, so which one of these terms that we have, enhanced quality service, time-sensitive networking, deterministic low latency, I said, which one of these, is the right term to use? And they went, yeah, funny story. They're like, we can't agree. We don't even know what to call the thing. More importantly, the concept of how it's going to work makes 0 sense, because what's happening is the device is putting out these reservations onto the channel saying, hey, I'm doing real-time traffic, voice, video, what have you, and so I want to be able to make sure that I can continue to send those frames when I need to send them into the future. So I'm just going to go ahead and reserve my time slot on the channel for a second, 2 seconds. I'm just going to keep reserving these things and going forward. The problem is, that's a Wi-Fi 7 thing. So it'd be like running into a restaurant and yelling that you have a reservation, but doing it only in a language that one other person in the place understands. Because we still have we still have 6E operating in 6 gigahertz. They wouldn't understand it. Wi-Fi 7, actually, if you can believe it, works at 5 gigahertz and 2.4. Who'd have thunk? My marketing people didn't, but it does. And so if you try this on a 5 gigahertz or a 2.4 gigahertz channel, you still have, 6 generations of Wi-Fi devices that wouldn't understand what it was saying. And so they could never make the thing work. So now this is recent is kind of a weird misnomer, but what we found out is this was actually rejected in October of 2023. This is no longer in the standard. It's not going to come out. It wasn't pushed to a future standard, because the problem is with backwards compatibility in Wi-Fi going all the way back to, we still support 802.11b. I'm just having flashback to meetings for the past 6 months, and I'm tired of having this conversation. But so this was rejected because as long as we're backwards compatibility until the beginning of time, this is never going to work. So this was rejected. So if you go look at our website and you read all about all this feature and everything I wrote, just know and understand that was published, happened to be before they rejected it. And so trying to unmake the cake is kind of difficult, as it turns out. So that one's rejected, so we'll put that down there, and then, you know what, just go away. So now, if you want to take a picture of the slide, this would be the one to take a picture of. So that's kind of my update. So everything that I said at Mobility Field Day 9 back in May of 2023, I've now walked it all back, and this is what we're left with. Now, in the last 7 minutes, I want to talk about what I want to talk about, which is PSD. This was nowhere in my presentation. I want to talk about it because I've had this conversation multiple times this week, and I want to try to get one story out there for everybody. And I've talked to some other people here, and they're all they're on board with this idea, and they're agreeing with what I'm saying. So hopefully you guys maybe agree, but if not, I will be in Prague in October, and I will do this all again. So PSD is 6 gigahertz. There's a lot of different variables that go into it. I made this chart to try to help me clear it up and make it easy to read and understandable, and you see how that worked out. But more importantly, I want to talk about these values right in here, the AP power and the client power. There's some PSD values and some EIRP values. Now these things work together. Now we're going to use these values as we're going to run some DB math. So everybody get out your CWNA hats, your ECSC hats, and we're going to do some DB math. So an LPI client has a -1 dBm per megahertz of channel bandwidth, which means that you take 1 dBm times by the channel bandwidth, and that gives you your operating powers in dBm. So in the case of a -1 dBm at 160 megahertz, you get -160 dBm, which is actually 0. And then that's 15 zeros, and a 1 in milliwatts. Yeah, actually, when I put it in the calculator, it just told me 0. I had to manually do this to try to get that many zeros after the decimal point. So obviously, that's not right. Scratch that. Okay. So I said, well, maybe, well, it's a -1, but that's the LPI client. I said, well, let's use the AP, because the AP is 5 dBm per megahertz of channel bandwidth. That way I'm not dealing with those negative numbers or anything else like that. And I said, okay, so let's do that math. So the math is 5 dBm per megahertz of operating channel, of the channel bandwidth. So what that means is you have 5 dBm times 160 megahertz, which is 800 dBm, or 1E plus 80 milliwatts. Well, now we all know what 1E plus 80 milliwatts equals. So I put that into a conversion chart because I was like, this was at 2 o'clock this morning. And I said, I'm not doing that math at 2 o'clock this morning. And what it told me, what it spit out of my calculator was, that is a metric boatload of wattages. Well, I think you see where I'm going with this one. That's not right at all. There's no way because, as it turns out, the R12799 was rejected. They didn't let me build that AP. So that is all the incorrect ways of doing PSD. That's not how that works. That's not how any of this works. Man, I should have had that video commercial. So let's talk about how it does work. So there's actually a step in here that most people don't know, don't think about. The first thing you have to do is you have to convert dBms to milliwatts first. You can't leave it in dBms. So there's a standard that's used and to reference it. And the reference figure is 0 dBm is equal to 1 milliwatt. So when you say that, now all of a sudden you're like, oh, so -1 dBm is just going to be, well, it's just a little lower. 5 dBm is going to be a little higher. So what those numbers are actually, -1 dBm is equal to 0.79 milliwatts. 5 dBm is equal to 3.16 milliwatts. So these are the maximum transmit powers. So now when we run that math, and we're just going to pick the AP because that's the one we actually kind of care about when you're designing, you're doing stuff. 3.16 milliwatts times 20 megahertz is 63.2 milliwatts, or 18 dBm. Now this is a number that I can agree with. 18 dBm sounds like something I would set on an AP. So yay, we figured out that math. Now, here's the other fun part. Actually, fun is a really subjective word at this point, depending on what your pain threshold is. Because if you take this and you live in the land of milk and honey, and you're running 160 megahertz wide channels, 3.16 milliwatts times 160 megahertz is 505.6 milliwatts, or 27 dBm. Now you'll notice it's 9 dB difference. Now, we do that because power spectral density allows us to focus on the signal to noise. As you double your channel bandwidth, you increase the noise. In the past, we weren't allowed to increase the transmit power to offset for that, so our signal to noise would go down while our SSI values stayed the same. power spectral density allows us to actually adjust for that. So that 9 dB happens to be because there's 9 dB of extra noise in a 160 megahertz wide channel. So now that's why we're doing this. At about 1 o'clock this morning, I was in Peter McKenzie's room discussing PSD, as one does at WLPC. You laugh because you know I'm right. And as Peter and I were talking, it kind of dawned on us, or dawned on him, and then he dawned it on me, and then I dawned some other stuff on him, and then we dawned a lot of stuff on each other. And this is the maximum that it can be. But how many people deploy APs at a transmit power that's less than the maximum? Hopefully there's a lot of hands. I do it because I want to have a little bit of more overhead, so in case I have to turn the power up because I miscalculated a wall or there was something else that was put in place, I want to be able to turn the thing up. If you start at 11, remember the amps. I'm glad I'm able to entertain you, Jennifer. If you start at 11, you can't go any higher. So what happens when you set the transmit power lower than max? Now, the problem is I can't give you an answer because we're not certain yet. So Peter and I, some other folks, have been coming up with some ideas, and we're going to go back into the labs and we're going to go test a bunch of this stuff, and we're going to try to see and figure out what does happen when you're running at less than maximum power. If you set a static power, does it adjust as you adjust the channel bandwidths? So I say this out loud to this group because, look, you guys can do the testing for yourself. You guys can figure out stuff that you might have a different way. And then the next time you come to WLPC, you submit a talk that says, hey, you know what? I listened to what somebody else said, and I said, I think I can test that. I think I can build upon that. Let me do it. And then I'm going to show up at WLPC and come stand underneath the bright lights and have to wear your sunglasses and tell everybody, you know what? This is what I've learned, how this operates in the wild. So, thank you.